the final speaker of the workshop, Liebeck, as part of his binary groups.
Thank you, Cheryl. Well, since Culver and I took over as organisers of this short workshop, I carefully organised myself to be the last speaker, so I can thank the organisers. And in this case, I want to mention two particular organisers of the whole programme. One is Kai Maggard, who we of course lost very sadly. But we did plan to have a special day for Kai in the middle of the programme, which I guess we're not going to manage now. But, anyway, I did want to just mention him. And then I do want to mention Culver, who's been our inspiration and driving force throughout the application and then the reapplication and the submission and the resubmission and the rewriting of this and that. So Culver's been our inspiration throughout, so thank you very much. Okay, so I thought I'd offer a kind of a bit of light relief to finish with. So binary groups. Let me tell you what a binary group is. So it's a kind of a permutation group. So I'm going to take a permutation group G on a set omega, and let's assume omega is finite. So okay, so let's take a integer r at least 2, and 2 r tuples of points of omega. So for, let's say omega 1 up to omega r. Let's just call that omega, and similarly for, say, delta. So these are both r tuples. We write omega twiddles with a 2 delta if we can pairwise map any 2 coordinates here to the corresponding 2 coordinates here by an element of G. So if for all, say, I1, I2, there exists a G in G such that sending omega I1 to, well, let's write it in tuple form. Right, so we can pairwise map coordinates to coordinates from omega to delta. Right, so that's being two r tuples being 2 equivalent, and then G is binary if whenever for any r, whenever 2 r tuples are 2 equivalent, then they're equivalent, then they're actually equivalent on the whole group. So so this is the definition of G. This permutation group G is binary if for all r and for all r tuples 2 equivalence implies they're in the same orbit under G. So let's write that as G equivalent or something like that. There exists an element of G mapping this R tuple to that R tuple. So that's a strange looking definition of a binary permutation group. Just for later reference, this number 2 is well, obviously it relates to the term binary, but there's a more general definition. Well, generally, we say G has complexity, let's say K, if when you replace 2 here by a K, the same condition holds. If if for all r at least k, omega is k equivalent to delta implies it's g equivalent, that they're in the same g orbit. So where does this come from? This comes from model theory. So this definition comes from Churlin, and I'll explain the relationship between this and some model theoretic ideas a bit later. But first I'd like to explore this definition a little bit, show you some examples and some non-examples, just so you can get a feeling for what that definition means. So examples, first, a very important example, a trivial one, but if G is the full symmetric group, so omega is just n, this is obviously binary because the two equivalence tells you whether omega I1, so if I can send omega I1, omega I2 to delta I1 and delta I2, then either they're distinct, they're both distinct, or they're both the same. And that's what you need to map one R tuple to another R tuple. The alternating group is not binary, so AN is not, because here's a couple of n tuples. So n is at least 2 here, I guess, and maybe at least 3 or something. So if we take that n tuple, this is 2 equivalent under the alternating group to the same n tuple if we just swap the 1 and the 2. It's 2 equivalent under AN, but obviously these are not in the same n orbit. In fact, AN has complexity n-1, the maximum it could possibly have. I should have said the complexity of k is the minimal possible k. So k is minimal, such that this condition holds here. All right, so let's look at some other interesting permutation groups. Let's say G is a symmetric group acting on K set, so let's say pairs. So Sn acting on the n choose 2 pairs. This is not binary. Very easy to see. So I can just produce a triple, a 2 equivalent pair of triples which are not in the same orbit. So if it's an obvious thing to do. So if I take, let's see, 1, so that triple is 2 equivalent to that triple. Okay, because well, obvious. Any pair of pairs intersects in one point, so you can map them to. But obviously the triples are not in the same orbit. What else do I want to? So in fact, this action has complexity 3. However, if you take, if you just slightly change this to ordered pairs, it does become binary. So a neat little thing. So if omega is the ordered pairs of distinct points, so n ordered pairs, then this example, the order of the pairs matters, and in fact pretty easy to see that this does become binary. So this, okay, this action is primitive, and this is not primitive. Right, just another few examples. So if you just, here's a whole class of binary groups. If you take regular action on omega, so it's transitive and the point stabilizer is trivial. This is binary. So how do I show this? Let's suppose that we have a couple of two equivalent R tuples. So then there exists, so then I can map omega 1, omega I to delta 1, delta I, because it's two equivalent, and because it's regular, the same for all I, it's the same G, right? There's unique G, so unique G. Okay, there's unique G sending omega 1 to delta 1, so that the same G will work for all I. Okay, so this G will send this R tuple to that R tuple. So that's a whole class of binary groups. What else? Okay, let's. I just want to have a whole other class. So if you take a full imprimative Reith product, you take SK Reith SM, let's say, where omega is just the the usual imprimative action. This is binary. I'll leave you to just think about that for a few seconds. It's clear, right? The two equivalence means that any pair here, if they're in the same block, then the corresponding pair here lie in the same block, and so that's pretty easy. And one final class of examples, some affine examples, some affine groups. So if you take an anisotropic orthogonal space, so V anisotropic orthogonal space, so that in other words there's a quadratic form on V for which only the zero vector has value 0. Okay, this would give us a class of infinite examples as well, but in the finite case these only occur in dimensions 1 and 2. Then if you take the semi-direct product of V with the orthogonal group of this quadratic form, okay, so that's an affine permutation group on V. This is, it's binary, so maybe I'll just quickly indicate why this is, because if you take an R tuple of vectors, you may as well start with each R tuple with the 0 vector, just for convenience. So we take, well, I guess it's an R plus 1 tuple. So let's suppose this is 2 equivalent to this R plus 1 tuple. So let's see, I can map 0 Vi to 0 Wi for all I. So that will imply that Q of Vi is equal to Q of Wi for all I. And I can map VIWJ to, no, VIVJ to WIWJ by an affine element here. That quickly, you see, implies that VIVJ, the corresponding bilinear form, is, these are equal. And so I'd like to use Witt's lemma to say, well, then there's an element of the orthogonal group sending this tuple to that tuple. I can't quite do that just from this fact. I need the dimensions of the span of this to be the dimension of the span of that, and for that you need this anisotropic condition. It's a very simple argument. Anyway, so Witt's lemma essentially says this. So this gives, in the finite case, examples just in dimensions 1 and 2, we get FQ extended by the orthogonal group in one dimension, which is just -1, or you can have FQ squared extended by the O2 minus of Q. Okay, so those are the some affine examples, and now there's let's write it up here. There's a 20-year-old conjecture that says I've already told you all of the primitive binary examples. So Churlin's conjecture, which is, probably existed quite a long time before 2000. He published it in a paper in 2000. Is that if you have a primitive, so lots of the examples I've told you are not primitive, but if you have a primitive binary group, then you've only got the things I've already told you. So you could have the full symmetric group. You could have a regular group. Well, the only regular primitive groups are cyclic of order p, so just generated by a p cycle. Or you could have one of these affine groups. So at the time he published this conjecture, there was, as far as I could see, absolutely no evidence whatsoever for this conjecture. There were no results classifying binary groups of any sort. So it's just an amazing insight, or I don't know. Yes, I guess it's an amazing insight to think that this would be all, because the conditions are a bit mysterious and hard to get a feeling for whether there should be lots of binary groups or primitive groups or not. Anyway, right. So now I want to show you what was behind Churlin's definition and behind this conjecture. Yes. So let me just explain the context. Okay, so it's very closely related, actually. If you were at Joanna's talk last week, it's very closely related to what she was talking about. So, okay, so the context is, in model theory language, relational structures. So what's a relational structure? This is a set, omega, which is going to match up with our omega we've read already, and a bunch of relations. And these relations are just subsets of omega to the Li for some Li, at least 2. So that's all the relational structure is. The type is just the maximal value of Li you have. So the type, so I guess we'll call a relational structure curly R. The type is the maximal max of Li. And naturally enough, we'll call it binary of this, so type 2. We'll call the relational structure binary. Okay, And so these relational structures have isomorphisms and automorphisms, which we want to introduce. So I guess I should write down the definition. So an isomorphism let's say phi from between two relational structures with some obvious notation. It's a bijection from between the two sets, just sending the relations in R to the relations in R primed in a bijective way. So rather than writing too many symbols down, let's just say Ri to Ri dashed bijectively, the usual, exactly what you would expect. And so we get an automorphisms, and we get an automorphism group. Of a relational structure, and of course that's a nice permutation group. Right. So now, what did I want to do now? Ah, yes. So now the types of relational structures which are interesting in Churlin's context are the homogeneous ones. So, so let's say if you have a subset of omega, we've got a substructure. Excuse me. So R sub gamma will be the subset gamma together with relations, say Ri dashed, where the Ri dashed are just Ri intersect gamma to the Li, right, the obvious things. And we say that our relational structure is homogeneous if any isomorphism between substructures extends to an automorphism of the whole thing, the usual kind of definition that Joanna showed us last week. So R is homogeneous if any isomorphism between substructures, say R gamma to R, gamma dashed, where gamma and gamma dashed are subsets of omega, extends to an automorphism of R. Okay, so let's look at some examples of homogeneous structures. I'm just going to remind you of the ones Joanna shown us, actually. So, so examples. So if we have we're just interested in binary structures in this talk, and let's say we only have one relation. So this is omega with one relation. This is just a directed graph, of course, right? Just got one set of ordered pairs, so we have a digraph. And there exists a classification of binary homogeneous digraphs. So this was in the 1980s, Lachlan. Let me remind you of there are quite a few families of homogeneous digraphs. It's rather a nice classification. Let me remind you of the case, just the case of graphs, undirected graphs. So so homogeneous graphs. So that was done earlier by Tony Gardner. And what are they? You just get the 5-cycle, you get the 3x3 grid, K3 cross K3, and then you get just disjoint copies of the complete graph, MKN, plus the complements. So very few. There are many more families of homogeneous digraphs. If you have more than one relation, so there we have omega with k relations, then this is just you can just think of these as colors, right? So then we have this is an edge-colored digraph. So there's no classification that I'm aware of homogeneous edge-colored digraphs. I think that's not really a feasible thing to do. But for example, we can have many more homogeneous structures here than just for graphs. Just let me show you a trivial example. So the hexagon is not homogeneous, right? Because we have two different types of pairs, like this pair and that pair. But if I introduce another color, I'm colorblind, so I'm just going to do dotted color. So if I have those two colors, then that becomes homogeneous with two colors. Okay, jolly good. So what's the connection of all this with groups and the stuff I was talking about before? There's a very nice right. So connection with I don't know, groups. So it's just a basic fact, pretty elementary as you might imagine, that if you have a group of complexity k, as I defined it, I've rubbed it off. So if you remember, complexity k means that if you have two r tuples, for any r at least k, if you have two r tuples that are k equivalent, then they're in the same orbit. So this is if and only if G is the automorphism group of some homogeneous relational structure of type K. Oh, terrible notation. Anyway, the type is the maximum number of tuples, things in the tuples that you have. Okay, so if we have complexity 2, that's our binary groups, then we're looking at, so G, let's write, so G is binary if and only if G is an automorphism group of a binary homogeneous structure, and that's, so we've just seen a homogeneous edge-colored digraph. So, oops. Okay, so R equals let's just write that. Okay, so that's why Cherlin was interested in this. Homogeneous relational structures form a massive topic in model theory. Much more in the kind of countably infinite case than in the finite case, but the finite case is kind of used in various results for infinite homogeneous relational structures. Anyway, Churlin is very interested in this. That's good enough for me. Okay. So, do I have Churlin's conjecture? Yes, I have Churlin's conjecture. So, let me, there wasn't much work on Churlin's conjecture. As I said, at the time he made it, there were hardly any results about it, just some sporadic computational results and so on. I guess that's kind of motivated his conjecture. But much more recently, there has been a lot of very nice work on Churlin's conjecture. We have a nice conjecture about primitive groups. Okay, some of us have been chugging away at these kind of things for decades, and there's a standard kind of procedure to try and carry out. So Wiscon's showed that if G is binary and primitive, then very few of the standard types of primitive groups can occur. It has to be affine or an almost simple group. Okay, and then Churlin himself, a paper published in the same year, I think, covered the affine case. So G is affine implies we just get this example coming from anisotropic orthogonal spaces. Right, so that leaves the field nicely, cleanly open for the almost simple case. So the aim now is to show that, well, from now on I'm going to talk about the almost simple case. So let's suppose we have a primitive binary, and it's almost simple. And according to Churlin's conjecture, we should prove that G has to be the symmetric group itself. That should be the only example. Right. So this was the point where Nick Gill was kind of being the leader of attempting to do this. So Nick Gill and Pablo Spiga have sort of published with some co-authors, have published some very nice papers on this. There are shall I announce the? Maybe I'll. So Gill and Spiga are kind of the pioneers for this, and I've kind of muscled in on the final act, and so maybe I'll state a theorem with a star. I'll explain what star means. So this is Nick and me and Spiga. So up to the definition of star, we have a proof of Churlin's conjecture. So what does star mean? Star means we still have a finite, quite a small finite number of cases to check. And so Spiegel is the magma king of this. Computation is a very effective tool for this. So star means there exists a smallish, a very explicit finite number of computations which are chugging away one by one, but they seem to take a very long time. So I was kind of hoping that by delaying the talk to the last possible moment, I would get a triumphant email from Pablo this morning, but no such luck. Anyway, so I'm hoping that maybe next week or the week after or whatever, the star will be removed. Anyway, I'm extremely confident that this is true, and moreover that the proof of it will be complete very shortly. So now, how on earth do you, basically you've got to show that nothing is binary, no primitive groups are binary. How on earth do you do that? So if you, I don't know, I kind of got interested in this conjecture before Nick Gill kind of fastened onto it. In fact, I told him about it, but I didn't have any great ideas. If you try it sort of directly, it's horrible. But Nick and Pablo had some brilliant ideas, and one of their most brilliant ideas, that there are a number of tools you can use to show things are not binary. Here's one of the major ones that they invented. So a major tool to show a group is not binary. When you see the lemma, it's trivial, but it's kind of a brilliant insight. So the lemma says that suppose you can find a subset of our set omega such that the group induced on this subset, so let's call it G upper lambda, so that is the stabilizer of lambda, and the group induced on it is doubly transitive, but not the whole of the symmetric group on lambda. So suppose you can find such a subset, then G is not binary. Okay, and the proof of this, as you can imagine, is rather trivial, but let's go through it. So let's say right, so let's say lambda has size t. G doesn't induce the symmetric group on lambda, so there's two t tuples that are in different G orbits. So say, excuse me, so we can order two orderings of lambda which are not in the same G orbit. So these are just orderings of the set lambda, but of course they're two equivalent because of this two transitivity. Okay, so that's it. But that one is two equivalent to the other one. Okay, so that's by definition, that says we have a couple of two equivalent T tuples that are not G equivalent. So G is not binary. Right, so that's all very nice, but you've got a random, you've just got some arbitrary primitive group. How on earth can you find two transitive subsets? Are there some? Are there lots? This is their great insight. There are lots. In an arbitrary primitive, well, almost simple primitive group, often you can find two transitive subsets. So let me show you one way you can do that. Well, first of all, let me give them a little more limelight about. So their definition of such a subset, such a subset lambda, they call it beautiful, and they are beautiful. It's a good definition. Right. So on the face of it, it's not clear why should a primitive group have lots of, or some beautiful subsets. So here's so this is Nick, Gil, and Pablo. If you have our setup, we have an almost simple primitive group. So well, it's not under the binary assumption. So G is sim omega is primitive and almost simple, and the socle of G is an alternating group. Let's say A, R, an alternating group. Then either there exists a beautiful subset, so you can find some two-transitive subset, or, well, virtually always you can find a beautiful subset. The only cases where you can't, when obviously if you have the natural action, if you have the action on pairs, which I had a brief look at right at the beginning, then you can't find a beautiful subset. And there's a couple of other families I won't go into. Very explicit. So two other families of very explicit actions of alternating groups. But apart from those, you can always find one of these two transitive subsets in which you don't induce the whole symmetric group. So they're very, not so easy to construct these, but they're abundant in an arbitrary action of an alternating group. Okay, well, so I won't show you how they prove their result. So I just want to show you something that I've had some contribution to. So here's, for groups of Lie type, the method they have there is not so it's very specific to alternating groups. So so here's a tool for producing beautiful subsets for groups of Lie type. It's another very elementary lemma. Okay, so yes. Okay, so I'll state it in general terms because it applies. So suppose we have a transitive permutation group, and suppose there exist subgroups let's say with point stabilizer, let's say M, and suppose there exist subgroups A contained in M and S not contained in M, so S is a subgroup of G not contained in M, A is a subgroup contained in M, and A is SL, so it's SL R of Q for some R of these two, and what else? A is contained in S, which is SLR plus 1, possibly over some center. Okay, so suppose you can find such subgroups in G, then you can produce a two-transitive subset. So then there exists a lambda contained in omega of size q to the r, on which we induce at least the affine special linear group, so a two-transitive action. Okay, so this may or may not be beautiful, but it's certainly two-transitive. Okay, the beautiful requires not the symmetric group. So anyway, potentially quite a big two-transitive subset. So let me quickly show you how that goes. It's another very trivial argument. So the proof is, right, so here's A. So A is SLR contained in SLR plus 1. So basically A is going to be kind of these matrices with a 1 inside. So this is R by R inside SLR plus 1. So this will sit inside some parabolic like that inside S, SLR plus 1. And well, this parabolic might be contained. I want this not to be contained in M. M is our point stabilizer. But either this parabolic or the one with stars here is not going to be contained in M. Because if both were, then the whole of S would be contained in M. And that's what I assume not to be the case. So, so this is, let's call this P. And then with P intersect M equals A, and then our subset lambda is just going to be the cosets of A in P, which can be identified with some cosets of M in G. Okay, so that's size q to the r. Pretty easy to see that we get the affine group induced on that. Okay. All right. So if so, we can get some pretty large two-transitive subsets, and usually they're these are beautiful because if you have, so for example, if you had, well, let's do some examples where we can apply this lemma to get beautiful subsets, and then that will probably be it. So let's start with a very trivial one. So if we have, say, PSLNQ, and the action is on, let's say, R spaces, R subspaces. So the stabilizer is parabolic. Something like that. Well then, what's our A and what's our S? So here we take A to be this SLRQ. Obviously in SLN, that sits inside an SLR plus 1 of Q, which is not contained in M. Okay, so SLR plus 1 of Q. So there we go. There's our lemma now produces this two-transitive subset lambda of size q to the r. Could we, so the only thing stopping this from being beautiful is if the group induced is the whole symmetric group, but the symmetric group of degree q to the r well, we have to do a little bit of argument, but usually q to the r is far bigger than the value of any symmetric group that can sit inside PSLN, right? Anyway, you need a little bit of argument to show that. Let's do another case. Let's do E8 of Q. So we need to consider all the primitive actions of E8 of Q. So there's a whole, we can do the parabolics in the same kind of way. Let's do, so here's my favorite maximal subgroup. Oh, how many? 1, 2. There we go. And there's the extended node. So let's do A1, E7. That's a nice maximal subgroup of E8. So what shall we choose for our A and our S? Well, let's just choose A to be this. Let's see. This guy. What's this? That's A6. So A is SL7. Clearly, from the diagram, that's contained in an SL. Oh, how many nodes do I? Yes. That's contained in an SL8, which is not inside M, right? S equals SL8. There we go. We get a beautiful subset of size q to the 7. Well, a two-transitive subset of size q to the 7. The symmetric group of degree q to the 7 is not involved in E8 of Q. It's far too much. Okay, so you can use this simple idea to rule out lots of primitive actions of almost simple groups, but it by no means works for all of them. So a major case where you need different arguments is classical groups, for example, classical groups in actions on C9 groups, right? This is an arbitrary, almost simple group with an irreducible action on the vector space. This is just an arbitrary, simple group, so you're not likely to find such a nice situation as in the lemma. So, well, we need completely different arguments for those, but I think I will call it a day there. Thanks very much.
One of your early examples was the Reef product.
Yeah.
Does that also apply to generalized Reef products?
What are generalized Reith products?
Is there a
Oh no.
They're very, very primitive.
Very, very imprimitive.
So you
You-
cutting things up, or you have things like rectangles and
Are you-
complicated relational structures.
You just iterate Reith products, are they? Iterated Reith products?
What we actually did was things that aren't just iterations. She said, I wanted to reply to all the okay,
All right, well, we can have a look later, yeah.
it would be nice to get some more examples. Yeah. So I guess the question is whether there are more primitive examples known of that type.
That's a mystery. Classifying the non-primitive binary groups is very much of interest and seems very difficult, but we'd love to be able to do something with that, yes. What about ternary? Well, there's hardly any model theoretic results on anything but binary structures. That Lachlan did classify the homogeneous ternary relational structures with one relation. But there are many, many families, but hardly any primitive examples. So if there was some motivation, one could try and push it further. But Cherlin seems more interested in asymptotic results about complexity of various families of primitive groups. Anyway, it seems to be very difficult to prove anything.